2.3, polynomial functions with higher degree and modeling. If you feel pretty good about doing transformations, then we're going to do transformations now on higher degree. And then we're talking about the tails and looking at the limits again from factoring. So now we're going to be looking at higher degree and doing those things. Graphing the transformations of monomial functions. So it's not a power function, but it still has one term, a monomial. What is the parent function of g of x? What would be the parent function? Yep, so we're going to compare it to x cubed. What are some things that are going on here? What are some transformations that are happening to x cubed? Abram? And so what kind of shift is that when you shift to the left? So it has a horizontal shift left 1 unit. What else is going on this? Mary. Very good. I see 4 is being multiplied to the function. Again, if it was with the x, it would be on the inside with x being raised to the third power. So that's the y value that it's being multiplied to. Y is about what kind of shift? Vertical stretch by a factor of 4. Vertical stretch. And that's all that's being done on that one. The next function, what is the parent function for this one? Emily, what do you think the parent function is for letter B? X to the 4th. Chance, tell me about one of the transformations happening to the parent function. Very good. If it's negating the y, that means it's reflecting over the x. You don't have to write down negating y, but reflect over x-axis would be the answer. I just like to remind myself that if I'm negating the y, it's over the x, and so on. And let's see. Sam, give me another transformation. Very good. The 5 is a vertical shift. Up 5 units. And the last one, Abram. So a horizontal shift right 2 units. So those ones you guys are good on. The next one is, those next 2 are different. And so you do see that you have an x cubed there. So it's going to still have the same behavior of what an x cubed would have. All right, so we're going to start by graphing this one. X cubed plus x. Remember that you use that little hi-hat symbol right there for any power that's higher. That would be the same one that you would use on your laptop. That's always used for exponents. It has the same shape as a normal x cubed. Just like x cubed, it passes through the origin. So why don't we graph as well? Let's graph y equals x. If that's what's affecting the graph, let's see what has happened. I'm going to go into y2 and graph y equals x. You don't have to do this, but I'd like to zoom in right here on the origin. Zoom, number 2. Zoom in, and I can see there's a little tiny cursor there. You would move it to wherever you want it to go, and then you would hit enter again. I'm going to keep it there. wanted to see really what's going on in there. And look at how that line just follows right through there, right there. It has that behavior of being y equals x very closely right there. So we have x cubed, it's a normal behavior, but the plus x at the origin is making it look more straight through there. There are no max and mins for this one. Let's see what happens when we substitute in x cubed minus x. So we can see some of those same behaviors. If it was positive x, it had a line that was going up. And again, I don't like how I can't see what's going on in there. So I am going to go to zoom 2 again and zoom in. You can see at the origin that you are having negative x affect the cubic. And we have that negative line that's going down here. This time we do have mountains and valleys. We have x-intercepts. We have 3 of them. On the other one, we only had 1 x-intercept. So you're going to have to get used to zooming in on your calculator because sometimes it has that hidden behavior. Is there anything else that I wanted to say on this one? Yes, let's calculate the max and mins. So we're going to go to calculate, and I'm going to calculate the minimum first, number 3. And so I need to give it left bound and right bound. If I'm trying to calculate the minimum, I need to be on the left-hand side and the right-hand side. Well, right now I'm on the left-hand side, left bound, so I'm going to hit enter. And then I'm going to arrow over onto the right-hand side of that minimum, hit enter again. And it's giving me the 2 arrows of where it's going to look for the minimum. It's looking between those 2 arrows, hit enter again. And I'm going to write down that the minimum is at 0.58 and negative 0.38. And then I'm going to look for the max, go back and do that again. Calculate number 4, a maximum. And it says that the max is at negative 0.58. And so we have some symmetry going on here, 0.38. Let's go down to the next part where you're looking at the end behavior of a polynomial function. So this was something that we did in Algebra 2 as well. The first thing that you want to look at is you want to look at the degree. Don't be tricked. If the polynomial is not going from least to greatest, you need to find the highest degree. The next thing you want to look at is whether it's even or odd. You can see on this that when it's even on the bottom, the tails are going in the same direction. That's easy enough to see. You're like, oh yeah, I know they're going in the same direction. It's positive, therefore it's facing upwards. That would be the next thing that you would look for, even or odd, and then is it positive or negative? The even one is easy, facing in the positive direction, facing in the negative direction. The next part may not be so easy to know which one is which. I know students have said stuff, but I can't remember what they've said now. There's only one way that I can remember whether these are positive or negative. Tails. That's what it was. Yeah. That's exactly what students had said. They said if I take and I put a point on the tails and then draw a line, that would show me that it's going up on that one. And then if I did it here, I would see that it's going down. That's true. That is exactly what somebody said. Here's my positive one, left tail down, right tail up, and then you just switch it when it's negative. Already we're going to be able to see what's happening with this function without even having to use our graphing calculator. Let's test this knowledge on the next one. It says graph the polynomial. I'm not graphing the polynomial. We don't need to graph it. Why do we need to graph it if we have all this information? And so we want to look at its end behavior. So the first thing I look at is what is the degree of this function? Emily, what's the degree of this function? 3. You look for the highest exponent. So I know it has a degree 3. It's odd. That's the most important thing, is that it's odd. And then I know that odd tails can go like this. Left tail down, right tail up, or it can go in the opposite direction. I just need to figure out which one of those it's going to be. So on quizzing and testing, when students write stuff like this down and then they actually circle the one that it is, hi, how you doing? Yep, that's the positive one. So there's my end behavior right there. I can tell exactly what's happening as x approaches negative infinity and positive infinity. If I had to look at it on a graph, it would look like this. It doesn't matter where it is. It's only about that end behavior. I'm looking for the end behavior that's talking about as x is approaching negative infinity, where is the tail going? The tail's going down here. As x is approaching positive infinity, where is the tail going? The tail is going up here. And that's what we're looking for. We're looking for the end, where it ends. It doesn't really end, but that's where it ends on our graph. So this is important now that we're into it. The limit notation has to be used to describe the end behavior exactly, not the algebra notation. You would say that the limit, and you go from least to greatest, as x approaches negative infinity. So I'm just talking about the yellow part. As x approaches negative infinity, what is the tail of the function? Goes next to it, of f of x. So the limit as x approaches negative infinity of f of x is going where? It's going to negative infinity. And then I have to talk about the other tail as well. So the limit as x approaches positive infinity of the function f of x. As x approaches positive infinity, the tail is also approaching positive infinity. And that's how you talk about the end behavior. Then you could check it on your graphing calculator and see if you had done this correctly. Example B, what is the degree of example B? What do you think, Chance? Very good. Don't get tricked. It's not in descending order, is it? The degree 4, here is my leading degree right here. So I know it's a degree 4. That means that it's even. So that means that the tails are facing in the same direction. We just don't know. We need to figure out, is it facing upwards or downwards, Sam? So it's negative 3, x to the 4th, so that we know that it is facing downwards. And so if I look at a graph and just do a rough sketch, it's going to have 3 turns, degree 4. Well, it may not because it doesn't have x cubed in here. But the most important thing is that the tails are facing downwards. And then it's got something that's going on in between there. I'm not really sure what's going on in between there because we are missing a term. It's not a power function where it would just look like a quadratic. So that's why I'm highlighting those tails, because that's where I'm looking right now. Okay, go ahead and write the limit. Test yourself. How can I write the limit for those tails? This time is g of x. And they are going to negative infinity for those tails. Okay. Finding the zeros of a polynomial function. We're looking for the zeros. So obviously, I'm going to set it equal to 0 when y is 0. When y is 0, I know that allows me to find the x-intercepts. If I let x equal 0, then it allows me to find the y-intercept. What do you notice about this polynomial? Something that I can do with this polynomial? Exactly. So factoring out something from all the terms. They all have an x in common. And so when I factor out an x, And now I'm down to a degree 2, so I can use quadratic formula or factor. And I know that there's factors. We have 3 and 2. 3 times 2 equals 6. And then -3 and +2 will add to that -1. When we solve this, we just set all 3 of these equal to 0 and solve. So for our 3 solutions, we get x equals 0, x equals 3, x equals -2. Find the zeros of the polynomial function. I believe that's multiplicity. Multiplicity. What does that mean when we are factoring? It means that you are getting a repetition of your factors. Like I only have 1 x minus 3. I only have 1 x plus 2. And I only have 1 x to the 1 power. Those are all to the 1 power. I have 1 of each of them. Multiplicity means you're going to get some repetition here. So it's going to matter if odd, if the multiplicity is odd, it's going to cross the x-axis. So all of these would cross the x-axis because they're odd multiplicities. If I have an even multiplicity, then it's going to bounce off the graph. It's not going to go through the axis. It's going to come down and approach it and bounce off. Or if it's going to come up and approach it and bounce off instead of crossing through the x-axis. So let's start by factoring this and solving. Again, we see we can factor out that x. This will factor. I'm looking for factors of 9. They're going to add to -6. I know it's x times x is x squared. Factors of 9. Well, it's not going to be 9 and 1. It has to be 3 and 3. So -3 plus -3 equals -6. And then -3 times -3 equals +9. And if I clean that up, I know that I have 2. Whoops. I have 2 of them. So I'm going to write them in their binomial square. So here we can see what's going on with multiplicities. I have 1 x. So x equals 0. I have 1 of those. And then I have x equals 3 twice. So this is an odd multiplicity, x. That means it's going to cross the x-axis. And then I have an even multiplicity here, so it's going to bounce off. So what degree is this problem? It's a degree, what, Sam? It's a degree 3. That means it's odd. That means that I am going to have left tail down and right tail up, or left tail up and right tail down. It's got to be one of those situations. It is a positive leading, so we know it's this one. I have all the information that I need just to sketch the graph. I know that it's going to be left tail down, right tail up. I know that it's crossing at 0, and it's crossing at, well, it's at 3. I've got zeros at 0 and 3. Okay, so I'm using the function. I'm gonna have to move that. It's coming up. It's crossing through here. It's gonna have to turn to go to the next 0. So when it turns and goes to the next 0, that was an even multiplicity, so it needs to bounce off at that place and then go up. No, it's not exact. It's just a sketch of a graph looking at the behavior of the tails, the end behavior, what's happening at the x-intercepts. So that's what multiplicity means. If it's odd, it crosses. If it's even, it's going to bounce off. Okay, for example 4, we are going to use our graphing calculator to find those x-intercepts. The intermediate value theorem just says that you have these 2 points and there must be a 0 between them. So we're going to graph this. I can see that it's not completely in my window. I would like to see what's going on down here. So I'm going to go to window. That is about your Y minimum down where the negatives are. So just going to change this to some number until I can see that minimum down there. Let us calculate this minimum. So we found the minimum, and there's some more stuff going on over here, but again, we can't really see what's going on. So I would like to zoom in over there and see what's going on. Zoom. Number 2 for in. It didn't look like it had any max and mins over here. Like there's one max right there and there's a minimum, but even that minimum right there, I can't see too good. So if I move the cursor over again a little bit, what will happen if I hit enter again? How far in am I getting? And you can see that there is a slight minimum there. So we're going to calculate this maximum and that minimum. You start with the maximum. Once you get your graph in there, see what's going on. I don't want to waste any more time right now, but you also have those intercepts. There would be one way over, and you probably would not have seen that there were actually 3 more intercepts here. So there's a total of, have we done x-intercepts in here for calculating? Have we calculated x-intercepts? Let's do it once just to make sure that we have some. So x-intercepts. You're going to do the same thing, and you're going to go to calculate, and we're looking for a 0. The 0 is about the x-intercepts. Again, it's going to ask you to be, I'm going to do the one all the way to the left. So I'm going to go over near there. Right now, I'm right on the x-intercept, but it's asking for a left bound. That means I need to be on the left-hand side of that. That would be on the bottom. If I'm on the bottom of the function, I would be on the left-hand side of the intercept. So when you're looking for x-intercepts, you need to be on the left and right of that intercept. Now it's asking for a right bound. So when I go up top, that means that now I'm on the right-hand side of that intercept. And hit enter again. And we see this one is at 0.50. Did I write down the other ones? No. And so you do have a total of 4 x-intercepts. I just don't want to go find them right now because I want to get to a word problem that's about maximizing. So 4 x-intercepts. I just don't want to look for all of them right now. Designing a box, example 5. This technique for example 5 is going to be very useful when you're doing word problems. I'm not sure if I stress that enough in Algebra 2. All right, so we are designing a package here. Let's see, a box that has a volume of 484 cubic inches. The squares are to be cut from the corners of a 20 by 25 piece of cardboard. and the flaps folded up to make the open box. What size squares should be cut from the cardboard? So we already know what formula we're going to be using. It says volume. What's the volume formula? How do I find volume? If area is length times width, I have a third dimension. What's it going to be? That's a square. What's the other variable that's going to draw it out to make it 3D? Length times width times height. Now it's not just a square anymore. It's been lifted up. All right. So I have this box, and I need to cut out the corners so that I can fold it up to make a box. So we know that this is going to be x by x. We're looking to find out what should x be. If I cut too much, it won't fold up into a box. So x is really the height. I should put it here. I mean, they're all going to be x's, but x could be the height. And then what is the length and the width? I see that this side is 20. What is it actually going to be? This is not going to be here. Those x's won't be there. So that'll be 20 minus 1x, 2x. So 20 minus 2x. Put my x out front. For one side, it would be 20 minus 2x. And then for the other side, it would be 25 minus 2x. And I'm going to graph that. Go back to my Zoom, standard window, and have x, and then times 20 minus 2x, and 25 minus 2x. And I definitely can't see what's going on here. So I want to see the top where the y max is. I'm trying 1,000. All right. So I can see the picture. There it is graphed. And I know that I don't want to go out. What's my window on? To 10. I don't want to go out more than that, because if the box is 20 wide and I try to do it more than 10, that means that there wouldn't be a box here. It has to be 10 or less. So my x value is good where it is. I know that the y value has to do with the volume. And so here, these are all different volumes. I want to know specifically at 484. So my volume is 484. So I'm just going to substitute in 484 for my volume. This is like the best trick you could ever learn about equations. Is it says that this equation is going to equal that equation. So if I go to y equals, and my second equation is 484, a horizontal line, and then I graph it, that's the volume I want right there, right at 484. So right here would be a good x value to cut the box, or right here would be a good x value to cut the box. So we're not looking for zeros. We're not looking for a maximum. We're looking for where these are intersecting. So I'm going to calculate an intersection, number 5. Where are they intersecting? And it says the first curve. Is the first curve x times 20 minus 2x? And yes, it is. That's the first curve. That's true. Is the second curve 484? Yes, that's true. It says the intersection will be at 1.22. So if I cut the box at 1.22, what are the units? Inches, then the volume will be 484. So my x could be 1.22 and the volume would still be 484. And then I would do intersection again for the other one. So I'm going to calculate number 5 and intersection. Let me go over near there. Again, it is asking me, is that your first curve? Yes, it is. Is 484 your second curve? Yes. I don't need to guess. I'm just going to hit enter. And it tells me that I could cut the box at 6.87 inches and still have a volume of 484. So really the big takeaway here is when you have equations and you have something on both sides, if you put it in there and you do the intersection, you're always going to find out what your x values are every time. Okay, 2.3 works.